Hello, so we are going to be starting VLSI design notes. We'll be using the notes provided by RPI by Professor Russell Kraft. This is the textbook we're going to be using to reference that. So this is exactly the same format as all the lectures that he's done, but I'm just doing it in bite-sized forms. So I've included this snippet because I wanted to show that the impact of technology has definitely impacted how students approach learning. And as you can see, like the worldwide market, it has increased a lot in value. And before the 1980s, the GPA average was 2.5, but now it's much, much larger. And it's because of the help that computers have assisted students with. So I think using your resources is really important because the previous generations did not have that help. Even this textbook that was printed has been revised and reordered. All right, so we're going to be talking about NMOS and PMOS transistors. What is N? What is P? N stands for negative. And the negative carrier is the electron, denoted with its negative sign on it. P, in the same way, P stands for positive, and that stands for the hole that electrons leave. And so there's two types of materials called N-type and P-type. And we're going to be giving an example of N-type. So N-type semiconductors, what is the majority carrier? Electrons, right? Because N-type stands for electron, for negative, and electrons are negative. They are the majority carrier. So then what is the minority carrier? P, positive holes. I'm also going to draw a diagram of what it looks like in the textbook so that you see the movement of the electrons. So see, it jumps out of the hole, it leaves a hole. And that's kind of how we've come up with the structure of the NMOS transistor. So NMOS stands for metal oxide semiconductor, and it's because of the connection that we have. So I like to think of the PMOS as a bubble going in with the zero. So as you can see, G is 0, just like how it's written in the schematic. That's something that helps me remember how to do it. And then MOS has no bubble. So there's a 1, not a 0. So different logics. There's two different types of logic that are emphasized in this course. One is dynamic logic, which involves time. But what we'll be looking at is static logic. This involves a direct, this involves any input pattern that takes you directly to the logic function you want to implement. This includes a pull-down network. So it pulls it down to the low logic. And a pull-up network. So the pull-up network pulls it up to VDD, which is the high value. VDD can be 3.3, 1.2. It just has to be larger than the low logic value. So in this case, it should be 0 for low logic. So for NMOSs, we use the pull-down network, and for PMOS, we use the pull-up network. And I'm trying to make sure I get everything across in my notes. So we're going to be going over an example, and I think this might help how you see the logic. So we have two transistors in series, and one is A and one is B. They're both NMOS transistors. So if we have two inputs, how many different combinations can we get? 4. And that is what we're going to model. We're going to manually see which ones will get us the values that we want. What does it output? So let's look at when both A and B are 0. If we look at it as a switch model, we're going to have 2 open circuits. This will make it 0. So now I'm cutting and pasting and creating the second scenario for the logic. A is 0, that means that will be an open circuit. B is 1, this satisfies the NMOS because it likes 1, it's a closed circuit. Great. Third scenario. A is 1, B is 0. That means B will be an open circuit for the NMOS. The last scenario, when A and B are both 1, this means that both A and B will be closed circuits. So current will be able to travel through from before the A transistor to the end of B. So what does this mean for us? This means that both A and B, both NMOS transistors, need to be on for the current to go through. And NMOSs are used for pull-down networks. So that means that that's what will help us for more complex logic circuits. So right now I'm writing the logic that we need. So A and B need to be on for this circuit to be pulled down. So let's take another example. This is my way of writing a truth table, but I'm using the switch model to do so. So still using 2 inputs, so that means we have 4 combinations. Instead of NMOS, what will it be when it's a PMOS? So I have a PMOS A and a PMOS B. What's going to happen? So let's look at the first scenario. A and B are 0. What does that mean for us? Well, for a PMOS, that means that both A and B will be closed circuits, and current will be able to pass through. Second scenario, A is 0, B is 1. Because they're both PMOS, we're interpreting this as a pull-up network. So it's going to be pulled up to the high voltage. So right, back to the second scenario. B will be an open circuit. Why? Because PMOS doesn't do well with getting a 1 from the gate. Third scenario. B is 0, so that means that's on. A is 1, so PMOS will be off. The circuit is broken. Fourth scenario, A is 1, that means PMOS is off. B is 1, that means the second PMOS is off. So we have two broken points in the circuit. So which one is the satisfied scenario that helps us? A is 0 and B is 0. So we can write both A and B need to be 0 for current to pass through, for the pull-up network to work. And I'm also going to write the function, and that's it.